Good evening, everyone. Today we have to start question number 5. So that is a February-March 2024. Okay, let's start with question number 5. Compound Q can be synthesized from chlorobenzene in 7 steps using the route shown in figure 5.1. Okay, so before heading towards the question, if you will work out these steps and their type of reactions and everything, then it will be very easy for you. So if we just look at the types in step 1, you see that this place there is a alkyl side chain gets substituted, so it means it's a electrophilic substitution, right? And then if you say there is the atomic oxygen over here, so which clearly indicates that over here the oxidation reaction takes place. Then in step 3, if you see that the CHO, which is if I open its structure, it's C double bond O and H, and it is turning into this thing, which indicates us that it's a nucleophilic addition reaction of an aldehyde. And in this nucleophilic addition reaction, if you recall the reagent is HCN with NaCN as a catalyst. In the same way, if you recall the reagent over here, so it's acidified, it's alkaline KMnO4 or acidified KMnO4 can be used, and then after this an acid has been added. Now if we move to step 4, in step 4 you will see that this CN is turning into carboxylic acid, so it means this one is a hydrolysis, and as an acid is formed, which indicates that it's a acidic hydrolysis, and for acidic hydrolysis we heat it with any acid, dilute acid. Okay, now if you see over here, this carboxylic acid group has the hydrogen is substituted with the alkyl chain, and here acidified methanol is used. So it means it's an esterification reaction, which we further called condensation reaction. Ester is being formed. So the name is called esterification and the type is condensation reaction. Is this understandable to all of you? You're still here. If any one of you has any confusion, please ask. Okay. Then in this step, if you see SOCl2 is used and this OH is replaced by chlorine, which means it's a nucleophilic substitution reaction. Okay. Now, if you see in step 7, this reagent has been added. And if you see this chlorine over here gets substituted from the nitrogen. So this is also a nucleophilic substitution where an amine group actually displaces the chlorine. That's what you have studied in your AS syllabus. Yeah, obviously, Hussein, the oxidation of CH3 makes carboxylic acid. That's what we have studied. But from AS, if you recall, we have studied that, methane is the most reduced level. On its higher oxidation level, the alkene and alcohols. And then higher than that, we have a aldehyde or ketone, and its higher oxidation level is carboxylic acid and ester, right? So that's what we have studied in the type of oxidations. So if it's getting aldehyde from an alkyl, so it's an oxidation reaction. So basically it's not a complete oxidation. Basically it's a partial one. That's why we are getting aldehyde instead of a carboxylic acid. Okay. Okay. So here we got the nucleophilic substitution. Okay. Now in part A, let's see what they are asking. Write an equation for the formation of the electrophile for step 1. So in step 1, if you see, methyl is being substituted, so it means, and they have used these two. So you can easily make the equation for the electrophile formation that alkyl halide, when reacts with the AlCl3, that chlorine breaks the bond heterolytically by taking away the electron of a carbon and gets bonded with the AlCl3, forming AlCl4 negative, and CH3, a carbocation is formed, so it's an electrophile. Is this clear to all of you? These reactions we have studied. Okay, now in part 2, complete the mechanism in figure 5.2 for step 1. The alkylation of a chlorobenzene include all relevant curly arrows and charges. Draw the structure of the intermediate. So if you recall that, if you see over here, the methyl group is being substituted at a carbon 2 with respect to a chlorine, right? So we will make the electrophile that have been prepared over here. Then we'll show the attack from here. After this attack, the intermediate has been formed. We will draw the intermediate where there we have a chlorine. Here we have a methyl group, and each carbon has bonded to hydrogen. So we'll show that hydrogen. And over here, we will draw a semicircle with a positive charge. So the carbon breaks the bond with the hydrogen heterolytically and provides the whole pair of electron in the middle. And as a result, we get this, the pi bond system gets substituted and the hydrogen ion is released. So I'm going to put a H positive over here. Is this understandable to all of you? Okay. Now step 3. Step 2 is an oxidation reaction. See, that's what we have identified over here, that step 2 is an oxidation, right? Construct an equation for the reaction in step 2. Use atomic oxygen to represent an atom of oxygen from an oxidizing agent. Okay, so we need to make an equation over here, right? So the equation can be drawn like this. If you see the reactant is 2-methylchlorobenzene. So benzene ring, over here chlorine, over here CH3. Then over here, I'm going to put oxygen, and then in the product, I convert the methyl into an aldehyde, CHO. So see how many hydrogens has been lost? 2 hydrogens has been lost, so they will form water. So if you see 2 oxygens has been used from this, one oxygen is bonded over here and the other oxygen comes over here. So to balance the equation, I will need to put 2 over here. Now if I have to write the same equation in the molecular form, so it's C6H4 because 2 hydrogens are substituted, C6H4Cl. And then I will write CH3 plus 2 moles of atomic oxygen forming C6H4Cl CHO plus H2O. Is this understandable to all of you? Yes, if any one of you has any confusion, please ask. Suggest reagents for the conversion of K to M in step 3 and 4. Okay. In step 3, we have decided that we are going to use HCN with a NaCN, or instead KACN has been used. So that HCN or KCN is basically a catalyst. Sorry, NaCN or KCN has been used as a catalyst over here. So you can write either NaCN or KCN, but remember this NaCN or KCN is a catalyst and the HCN is the reagent. Okay, for step 4, it's a hydrolysis, and I have mentioned that we are going to use aqueous hydrochloric acid, right? See, that's what we have mentioned over here. Okay. Identify the type of reaction that occur in step 5. Okay. So in step 5, as I have told you, the type is condensation. The name is called esterification, but they ask you the type of a reaction. So if you write the esterification, it is considered as wrong. You have to mention that this is a condensation reaction. Is it to all of you? Okay. Now step 6. Step 7 takes place when P is heated with a weak base such as K2CO3. Okay. So this is why a strong base such as NaOH aqueous is not used for this reaction. So it's, I think, yes, it is condensation because water molecule is released. Yes, Mavin, what you were asking to be repeated? Okay, step 5. So if you see over here in step 5, see, if you see, this is a carboxylic acid, and instead of carboxylic acid's hydrogen, we get this CH3 group over here, right? Which means that, see, an ester is formed. So the reaction by which ester is formed, that type of a reaction is condensation. The name of the reaction, we call it esterification. But esterification is, remember, is not the type of the reaction. So if the examiner asks you to write the type of the reaction, you can write it condensation. And beside this reaction we have studied in, A2 level as well with the carboxylic acid derivatives, and where we have mentioned that these are addition elimination reactions. So instead of condensation, you can write it is an addition elimination reaction as well. So this one is also going to be considered correct if you write addition elimination. But as they are asking you to write the type of a reaction, and if you write esterification, so remember, esterification is not any type of a reaction. It's just the general name given to a reaction because the product formed over there is a ester. Okay. Okay. So if you see over here, when this reagent has been used with the alkyl halide, because why I'm saying it's an alkyl halide, because if you see this chlorine, which is bonded to an alkyl carbon, gets substituted over here by this group, right? So it's a nucleophilic substitution. Now, what they are saying suggests why a strong base such as NaOH is not used for this reaction. So if you recall, if there is an alkyl halide and if we use aqueous NaOH, so what aqueous NaOH do? Then this would not happen. Instead, this carbon is bonded to a OH. That's what you have studied in your AS level. So when there is a strong base, so that strong base itself acts as a nucleophile, and as a result, we are getting a OH over here. And another thing over here beside this, it's an ester, right? And ester can undergo hydrolysis with the aqueous sodium hydroxide because it's a strong base, and we use a strong base for the hydrolysis of esters. And here ester is present over here. So it means we need any reagent which do not affect or which do not react with an ester, right? So I think the more appropriate is to write that ester has been hydrolyzed if we use a strong base. So strong base reacts with ester and hydrolyze. Is this clear to all of you? Yeah, both are considered as correct. It's around going to be in 60s. Yeah, that's why we use weak base. So weak base, due to the weak base, this group is going to be substituted on this position. It can substitute chlorine, and there will be no effect on this one because in Q, ester is there. So instead, if we use NaOH, then obviously we will not going to get over here an ester. Okay. Now, part 8. Q is an optically active okay. Explain the meaning of an optically active. So there are two things which are very important. Optically actives are the one which have some biological activity, right? And the actual definition is the one which can optically active compounds are those which can rotate the plane polarized light. Okay. So optically active substance can rotate the plane, yeah, which can plane polarized. 1 minute, I'm going to discuss that is 1 minute, Abdullah. Polarized light. Give two reasons why it might desirable to synthesize a single optical isomer of a Q used as a drug. So there is a two reason. One is that if we prepare a single isomer and the drug has only one isomer, so we need a lesser dosage to give it to a patient, right? Dosage of drug needed dosage of drug needed in lesser amount. That's what I've told you that the optically active compounds are those they have a biological activity, and that's why they are used as a drug. Yeah, obviously the other isomer have a side effect. So if we get a one isomer, so we need a uh, lesser amount of that drug. The other is that the other isomer has side effects. Very good, Azif. Okay. Now part B. Q is commonly used in conjunction with aspirin. Okay. Aspirin is a weak bronchodilator acid. The pK of aspirin is 3.49. 75 milligram of aspirin dissolves in water to form 100 centimeter cube of aqueous solution. Calculate the pH of this solution. Okay. To find the pH, we need the concentration of hydrogen ions, right? So, but here we are given with the pK, and to calculate the hydrogen ion, we need the value of Ka, right? Because for a weak acid, whenever you need to calculate the concentration of hydrogen ions, the concentration of hydrogen ion is equals to under root Ka times concentration of acid, right? So K can be calculated from here because they have given you pK. So if you recall the formula, pK is equals to minus log 10 Ka. So if you have to calculate the Ka is equals to 10 raised to the power minus pK. So Ka is equals to 10 raised to the power minus 3.49. Can anyone calculate it and tell me the answer, please? Yes, please. Can anyone calculate and tell me the answer of Ka? 3.236 exponent minus 4. It's 3.3236 exponent minus 4. Now if I have to find the concentration of acid. So the concentration of acid is equals to moles over volume, right? Moles over volume. And here we have given with the mg. So if we have to convert this volume mass into grams, so 75 divided by 1000. And then MR is 180. So 75 divided by 1000, or I can write it like this, 75 exponent minus 3 over 180 gives me the mole, right? So 75 exponent minus 3 over 1000 gives me the mole, divided by 100, which is in centimeter cube, over 1000 to turn it into a dm cube. So can anyone calculate it and tell me the answer, please? What value of acid concentration we are getting? 4.17 exponent minus 3. Okay, thank you, Azif. Because 75 is an mg, right? And whenever we calculate the moles is equals to mass upon mr. And here the mass, we always use that mass is in gram, not in milligram. Okay, Maham? So that is gram and that is mg. Okay. So 4.17 exponent minus 3. So we got the concentration of acid. We got the concentration value of Ka. So the concentration of hydrogen ions is equals to under root Ka, which is 3.236 exponent minus 4 times concentration of acid, and the concentration of acid is 4.17 exponent minus 3. Can anyone calculate the value, please? Multiply them and take the under root. You will get the concentration of hydrogen ions. I didn't understand, Mahmin, what you were asking. We divided with 180 to convert it into a mole. See, from here we are getting the moles. And then when we got the moles, see, this is for moles, 1 minute. We convert it into a grams, then divided, okay, my bad. Here it's 180. 75 exponent minus 3 grams divided by 180 gives me the moles, and then divided by volume in decimeter cube, 1000 over 100 over 1000. Okay. Here, what answer we are getting? I mean, 0.000116. So that is the concentration of hydrogen ions, right? Now we got the concentration of hydrogen, and now we will put it in the pH. So pH is equals to, see, that's not 1000, Abdullah, that's 180. Okay. We have grams, we have divided with the MR to convert it into moles. Okay, Hassan. So it's 2.93, right? So minus log 10 times concentration of hydrogen ions, and we know the concentration of hydrogen ions now, minus log 10 times 0.00116. So we are getting 2.93 or 94. Yes, is it 2.93 or is it 2.94? Abdullah, calculate it again. You are doing some mistake in the calculation. Okay, thank you, Maham and Hussein. You are doing some mistake in calculation. You will be getting 4.17 exponent minus 3 over here. Okay, now part 2. Aspirin undergoes acid hydrolysis in the stomach. Give structure of the organic products of the acidic hydrolysis. Okay. So let's have a look at the structure of aspirin first. See, it's over here. Let me draw it over here. If you see, aspirin has a one benzene ring. On benzene ring, there is a one carboxylic acid. And on second carbon, there is an ester, right? So as we know, when the hydrolysis occurs, the ester bond or the amide bond is broken from here. So it means after this, we got one organic compound like this. Here we have a carboxylic acid already. So the OH gets bonded with the H forming alcohol. And the other compound, we got this part. So this is a C double bond O. So from with C double bond O, OH of water has been bonded. So we got these two products. Is this clear? That is the formula, Mehveen. Whenever you need to find the concentration of hydrogen ions of a weak acid, then we use this formula. Heating with the hydrochloric acid, if you are asking for this reaction that it is converting into these two, you need to heat with the See the hydrolysis. Okay. See, there are, okay, I'll share the notes with you guys as well. Let me show you over here the hydrolysis. Where it is. So basically, yeah, in hydrolysis, see, these are the compounds which undergo hydrolysis. Nitriles, esters, amides, and alkyl halides. Okay. And all of these, this bond has been broken. Is this understandable to all of you? Then, if I talk about this one, when this bond is broken, the organic part R gets bonded with the OH and we always get a alcohol when hydrolysis of an alkyl halide occur. Is this clear to all of you? Now, in these three cases, when this bond is broken, this C turns into carboxylic acid. This C double bond O also turns into carboxylic acid. And this C double bond O also turns into carboxylic acid. So in these three, we get one common thing, that is a carboxylic acid. That's what we get when acidic hydrolysis has been done. Okay, this nitrogen in acidic hydrolysis, it will turn into a ammonium ion. This one turns into an alcohol. And this nitrogen also turns into ammonium ion because it's an acidic hydrolysis. Is this understandable? And if the hydrolysis is a basic, an alkali has been used, so instead of an acid, we get the acid, we get the salt. Instead of a carboxylic acid, we get their salts. And here, instead of amine, ammonium ion, we get the ammonia. And here also, we get just the amine. Is this understandable now? So I'll share this note with you guys. You can easily go through the hydrolysis and the few examples, the general reactions showing which bonds are broken. Okay. What you want to be repeated, Sharia? Yeah. So the instead of carboxylic acid, we get its salt, and when it's an acidic hydrolysis, we get a carboxylic acid. The one after acidic hydrolysis is the alkaline hydrolysis. Now see over here, you can see the comparison over here. Sharia, it's a nitrile. This bond is broken, and the hydrolysis is acidic. We get the carboxylic acid, and this nitrogen turns into ammonium ion. Now, if instead of acidic hydrolysis, we have performed a basic hydrolysis, so carboxylic acid is not formed. Instead, its salt has been formed. Like if we just use OH, so we just remove the H positive over here. If we use NaOH, so we put a Na instead of a hydrogen over here. And if we use potassium hydroxide as an alkali, we put a potassium over here. And now ammonium is not formed. Instead, ammonia is formed. In the same way, if you look over here, it's an ester. This bond is broken. This carbon turns into carboxylic acid over here because it's an acidic hydrolysis. And if you see, this carbon turns into carboxylic acid salt because a basic hydrolysis has been occurred. Yes, is it clear to all of you? Okay, I'll share that note after the class. Okay, now question number 6. Amino acids are a molecule that contain NH2 and COOH functional group. Glycine is the simplest stable amino acid. So let me write its formula in the displayed form over here. You see there is a carbon. That carbon has a 2 hydrogens. On one side, we have a NH2 group. On the other side, we have a carboxylic acid. That's why we call it amino acid. So see, the isoelectric point of glycine is 6.2. It means that at pH 6.2, this glycine exists as a zwitterion because it has a no net charge. So in the form of zwitterion, it becomes NH3 positive over here, CH2 and COO negative. Yes, very good, Maham. So define isoelectric point. So we will write that it is a pH at which amino acid exists as a neutral species, or you can write it's a zwitterion. No, it's NH2. So in acidic condition, it turns into NH3 positive, not NH4 positive. It's already NH3 with no charge, then it will turn into NH4 positive, Maham. Okay. Yes, I am repeating that if the isoelectric point of glycine is 6.2, it means that at 6.2, exists as a this structure, not this, because at this pH, it usually exists as a zwitterion. Okay. And remember, if the isoelectric point is 6.2, so if we have a lower pH than 6.2, then it is considered as the acidic medium for that amino acid. And if we have a higher pH than 6.2, then it is considered as an alkaline medium for that amino acid. Is this understandable? Okay, so it means that pH 4 is going to be acidic, which means that here it is going to have a more hydrogen ions in it. Now let's have a look at a structure at a 6.2. At pH 6.2, its structure is like this. So now it has a more hydrogen ion. So it has a NH3 positive. So this nitrogen does not have ability to accept a hydrogen because it is already positive. But this oxygen over here is a negative. So it will accept the hydrogen ion. So at a pH lower than its isoelectric point, its structure will gets like this. Yes, and in alkaline, if the pH is greater than 6.2, then this part stays COO negative, and from here the hydrogen is released, and it will become, the structure would be like this: H2N, CH2, COO negative. If it is at pH greater than 6.5, because it is considered, greater than 6.2, because it is going to be considered as an alkaline pH for this amino acid. Good, Maham. Is this clear to all of you? Okay, now next part. B. Figure 6.1 shows two synthesis starting with glycine. Okay, if you see over here, isn't it? Let me show you that this nitrogen has a two hydrogens over here, and over here CH2, and then COOH. So what happens over here? That this hydrogen is actually substituted with the CH2, CH3, and this hydrogen is also substituted with the CH2, CH3. Right? So it means 2 moles of C2H5 Br has been used. Yes, Mavin? The class is recorded. And I'm going to upload it as soon as the class will end, okay? Now, if you see in the reaction 2, this is from glycine and we got this. So it clearly indicates us, as you see, that bromine is there and that bromine gets removed from here, and the rest of the part, that is C2H5, has been bonded with the nitrogen. And see over here, this whole group is bonded to the nitrogen. So it means that over here, the other reactant is CH benzene with C double bond O, Cl, or with C double bond O, Br. And that Br gets removed from the carbonyl, and that carbonyl is being bonded with the nitrogen. Yes, I just made the displayed form of this one, Abdullah, that if you see, there is a CH3, CH2 and CH3, CH2, which means C2H5. So there are these two groups. So it means that 2 moles of this has been used with this, and as a result, both of the hydrogens get substituted, and we got two alkyl chains over here bonded to the nitrogen. No, we can't use OH because with the OH, it's with the acid, its reactivity is very low, but with the acid chloride or acid bromide, the reactivity is very high because these are the carboxylic acid derivatives. Okay. Okay. Now, so it's you can call it addition elimination, or you can call it condensation reaction. And this one is a nucleophilic substitution. Okay. An excess of aluminium LiLH4 has been used in reaction 3, which means it's a reduction reaction, right? And LiLH4 reduces amide. LiLH4 reduces carboxylic acid. So remember, when there is a amide, amide is reduced to amine. And when there is a carboxylic acid, it is reduced to alcohol. Yes, very good, Maha. Okay. So it means that the most probably structure over here is that this C double bond O, this oxygen has been removed, and we get a NH, and this carboxylic acid turns into alcohol. Is this clear to all of you? No, aldehyde is basically the intermediate product. For that, we have to need a very controlled condition. If examiner specifies something like that, that we are getting an intermediate product, then we will make an aldehyde. Otherwise, it will end up to, the reduction will end up to the alcohol only. Okay. Now, state essential conditions for reaction 1. So, with the reaction 1, as we are using amine, so amine and with the ammonia, if you recall, when we react a alkyl halide with the amine and ammonia, we react a ethanolic condition. The reaction has been occurring in ethanolic solution. And under high pressure. or instead you can use that heating in a sealed tube. That's what we have studied. This is the reaction from AS. Okay. Now, identify the reagent used in reaction 2. So, as I have told you, we have identified it a benzene with the acid bromide or acid chloride. So you will write over here C6H5 COBr, or you can write C6H5 COCl. Now, draw the structure of the organic product U that forms when hippuric acid reacts with an excess of lithium aluminum hydride in reaction 3. So that's what we have already figured out, that there is a benzene ring. And then we got a amine over here. And then we got an alcohol. See, is this clear to all of you? Okay. Now B part 4. A molecule of phenylalanine R. Okay, that is a phenylalanine. React with a molecule of a glycine. Okay, this is a glycine. To form two dipeptides SNT. SNT are the structural isomers. Okay. Draw the structures of these dipeptides. The peptide bonds should be shown fully displayed. So it's, you know, if you have to show two dipeptides, what you can do. In first case, for example, you are bonding this OH, this CO with this nitrogen, right? So let's do this. So see what will happen. I will put a H2N over here. Then over here, C double bond O. Keep the rest of the structure as it is. And with C double bond O, I'm going to put bond on nitrogen, which has bonded to 1H because 1H has been substituted. And then this group. Is this understandable to all of you? Now, for the other isomer, I will swap them, which means that instead of now, I'll keep the carboxylic acid over here and then nitrogen over here with the one hydrogen and keep the benzene ring this. And this nitrogen is going to bond with this C double bond O. Now these two will getting bonded. So C double bond O and then CH2 and then NH2. So see, we got two structural isomers. Is this clear to all of you? What we did, that is very simple thing. With the carboxylic acid of a one molecule, we have reacted the amine of the other molecule. Yes, see, that's what happened over here. That's what I did over here in this case. In first case, what I did, I reacted this carboxylic acid with this NH2, and this amide group has been formed due to the reaction of these two sites. Now, if you look at the compound T, I have reacted this carboxylic acid and this amine over here, if you see. And as a result, we get this one. So that's how we are able to make two different, isomers. Now, part C. A student proposes a synthesis of a hypuric acid by the reaction of benzenamide, okay, with chloroethanoic acid. The reaction does not work well because benzamide is a very weak base. Explain why amides are weaker base than amines. So it's very easy. If you guys recall that the lone pair of nitrogen in amide is withdrawn or delocalized with C double bond O, and as a result, that the lone pair is not as readily available as it is available in a amine, right? So that's why they are weaker bases. Now part 2. The pK of chloroethanoic acid is 2.86, whereas the pK of ethanoic acid is 4.76. Chloroethanoic acid Cl CH2CO2H and ethanoic acid CH3CO2H. Explain the difference between these two pKa. Okay. Okay, it's for 2 marks. So I have to mention over here. Sorry, I missed it. So the lone pair. I have written that down, but I have explained it, but didn't mention. Yeah, you can write it, but you have to explain it properly. That oxygen is more electronegative. The oxygen on a carbonyl carbon is more electronegative. That's why the electrons are withdrawn. And as a result, the lone pair's availability decreases on nitrogen, which makes it less weaker base or weaker bases than ammonia. So the lone pair of nitrogen is not readily available to accept H positive. Okay. Now we have to explain the pK differences. So one thing that its value is smaller, which indicates that chloroethanoic acid is stronger acid than ethanoic acid because chlorine is electron withdrawing causes OH bond to get weaker, hence H positive ion releases more readily. Is this understandable to all of you? And as the hydrogen ions more it releases more readily, so it has a more hydrogen ions, and as a result, it is more acidic. Now, part D. Compound V is another amino acid. The proton is NMR spectrum of V shows hydrogen atoms in 5 different environments. Okay, so see, they have shown you the 5 different environments A, B, C, D, E. They are given these. Complete table 6.2 for the proton NMR spectrum of V taken in CdCl3. Table 6.1 gives some relevant data. Okay. For A, if you see, it's a carboxylic acid, right? So its range is going to be 9.0 to 13, right? And as it is bonded to oxygen, so there is a no, splitting. So it is going to be a singlet. Is this clear? Now B, they have mentioned you that it's multiplied, but you see these are the hydrogens which are bonded on the benzene ring. So attached to aromatic ring. So its chemical shift is 6.0 to 9.0. Okay. Now if you look at C, C is the one which is neighbor to the benzene ring, right? and on one side it has a two hydrogens on its other neighbor. So if it has a two hydrogens on the other carbon, so it's going to be 2 plus 1 gives you 3. So it is going to be a triplet. And the signals for this one is also going to be a triplet, because on one side it is bonded to a carbon and that carbon has a two hydrogens, so 2 plus 1 triplet. And E, it is going to be a singlet because the hydrogens are bonded to a nitrogen only. So over here I will write triplet, triplet and singlet. Is this clear to all of you? Now, if you look at C, C is a neighbor to the aromatic ring. So alkyl next to the aromatic ring, its chemical shift is 2.3 to 3.0. Yes, it normally comes every week. Yes, which one, Sohaib? If you look at C, C are these two hydrogens, right? And they are neighbor to benzene ring. It's a proton NMR analytical chemistry. We have guys have a recordings of it in YouTube as well. So see, it's neighbor to alkyl ring. Okay, so and on the neighboring carbon we have a two hydrogens. So splitting pattern will always be identified by n plus 1. So n is always the number of hydrogens on the neighboring carbon. So these hydrogens are bonded to this carbon, and this carbon is actually the neighbor one, and it also has a two hydrogens. So the value of n is going to be 2. So 2 plus 1 gives you 3. So that's why it's triplet. Same goes with the D as well. On the left, it's just a benzene and it has a no hydrogen. So we are going to see the right side, okay? But if the carbons are on both the sides, so we'll look onto both the carbons. No, as if this carbon, how this carbon has a hydrogen? This carbon has a one bond over here, second bond over here, third bond over here, and the fourth one is involved in the pi bonding. So this carbon doesn't have any hydrogen, but this carbon, so see, one neighbor is this one. The neighbor one has no hydrogen. The neighbor two has two hydrogen. So that's why 2 plus 1 is equals to 3. Now, if we look for these two hydrogens, these are bonded to this carbon. On neighbor of this is the carbon which has two hydrogen. On the other side, the neighbor is nitrogen. So we will not look or consider this nitrogen. Okay, Asif. So that's why triplet, triplet, and singlet. Okay. So it's next to alkyl aromatic ring, which is 2.3 to 3.0. Okay. Now, if you look at D, D has bonded to an electronegative atom, right? So see, alkyl next to electronegative atom. So CH2 bonded to N. So its value is 3.2 to 4.0, its chemical shift. So I'm going to write 3.2 to 4.0. Is this clear? No. If there is other atom bond on the neighbor, then we cannot count their hydrogens. The only neighbor hydrogens are counted if the neighbor is a carbon and that carbon has a hydrogens. Okay, E is a singlet, E is NH2, right? So for nitrogen, it's an amine. And if you find amine over here, see, amine, it's 1 to 5. So the chemical shift value ranges from 1.0 to 5.0. Is this clear? Okay, now part 2. Complete table 6.3 by placing a tick to indicate any protons whose peaks are still present in proton NMR of V taken in D2O. So remember, in D2O, the OH hydrogen and the NH hydrogen are being replaced. So if you see A is a C double bond OOH, right? So it means this hydrogen is going to replace by D, and E has a NH2. So these hydrogen are going to replace by the D2. So these two are going to be replaced. So it means I'm going to put a tick on B, C, and D. Is this clear to all of you? Because if the neighboring are the carbons and those carbons have a hydrogen, they get the splitting pattern. Some other element is bonded, then there will be no splitting pattern. That is the rule that you need to remember during the exam, okay? So here we have ended the paper. I'm going to just upload it in a few minutes and wish you all best of luck for tomorrow's exam. Okay. Yes, Abdullah. No, there is. Let me show you. I've shared the file with you guys, right? I've shared the whole, I think, zip file over here, over there in the group. See, there are two parts, 14 analytical chemistry 1 and 15 analytical chemistry 2. See in the zip file, is there 15 analytical chemistry 2 file is there or not? If its file is there, then you will find the proton NMR. Check Abdullah and tell me, please. I made the zip from this folder only. Okay. So when we use D2O, if you recall, D2O only always displaces the bonds, the OH bond, the hydrogen bonded to H and the hydrogen bonded to O and the hydrogen bonded to N. So in this structure, if you see over here, this is the hydrogen bonded to A, bonded to O. So the A is going to be displaced. So that this signal is going to be disappear in D2O. Over here, these hydrogens are bonded to nitrogen. So these hydrogens are going to be displaced by the deuterium. And as a result, the signal is also going to disappear in the deuterium. So we are left with B, C, and D. So that's why I put up tick over B, C, and D. Yes, the hydrogens bonded to nitrogen and the hydrogens bonded to oxygen, their peaks are removed or disappear. It is because the hydrogen is displaced by the D, the other isotope. No, not CDCl3. In CDCl3, these peaks are there. See, if you see over here, they have mentioned that initially we have taken it in CDCl3, so that's why we are getting all the signals. But when we put a D2O, then these two signals are going to disappear because these hydrogens are bonded to oxygen or nitrogen. Okay. So wish all of you best of luck for the exam. May Allah give you success to all of you. And I will be responding to your queries. Okay. So you can WhatsApp me. Okay. Take care. Goodbye. Allah Hafiz.